All right, hello everyone. I know you've always been wondering how long would it take, or how do aliens get to dinner when they're on the moon? Well, now we can find out. So, we have our moon, and I have some aliens that are whizzing by. Turns out they're headed to Earth for a dinner. And we know their velocity when they're at the moon. Their velocity is 20,000 kilometers an hour. And we know that they have to be there in t equals 38 hours. Okay, so the problem kind of gave us a little bit of a hint. It said, what deceleration must the aliens apply so that they come to rest in time for their dinner? Okay, so let's see if we can express the aliens' velocity as a function of time. So the aliens' velocity as a function of time equals their initial velocity, v naught, and then if they're traveling at constant acceleration, then each second we will have a velocity contribution through this acceleration. Notice I kept it positive. We know that they're going to apply a deceleration, i.e. a negative acceleration, but my equations should respect that if I do everything carefully. Okay, now what do I know? I know that at v of t equals 38 hours, if I evaluate the velocity at this time, it better be equal to 0, right? Because they're coming to a rest in 38 hours. So then this would be 20,000 plus a times 38. Okay. So notice my acceleration is measured in kilometers per hour squared. It has to be, because I multiplied hours right here, and my velocity is in kilometers per hour. So this whole term has to come out as kilometers per hour as well. So I can solve for my acceleration. Acceleration equals negative 20,000 divided by 38. And that equals negative 20,000 divided by 38 equals negative 526. And then the units are going to be kilometers per hour squared. So this is the average deceleration that the aliens would need to apply to be at the Earth in time for their dinner. Another way you could do it, if you could express x of t for the aliens, then you know that x of t equals 38 hours. At this time, let me call this lowercase d. At this time, they better be at this distance, which we're told is 380 times 10 to the third kilometers. At that same time, they better be located at the Earth. And if you do this, you'll get the same answer. So kind of we have two ways of doing it. Because we know they come to rest at the Earth at this time, then we can either force them to be at rest at that time or evaluate their position at that time. And we should get the same acceleration for both for this to be a physically reasonable problem. But that's the answer. Negative 526 kilometers per hour squared.